Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young.
Chapter 5, Conic Sections. Section 41, Definitions, Pascal's and Brianchon's Theorems. Definition: the set of all points of intersection of homologous lines of two projective, non-perspective flat pencils which are on the same plane but not on the same point is called a point conic. Figure 49. The plane dual of a point conic is called a line conic. Figure 50. The space dual of a point conic is called a cone of planes. The space dual of a line conic is called a cone of lines. The point through which pass all the lines or planes of a cone of lines or planes is called the vertex of the cone. The point conic, line conic, cone of planes, and cone of lines are called one-dimensional forms of the second degree. The following theorem is an immediate consequence of this definition. Footnote: all the developments of this chapter are on the basis of assumptions A, E, P, and H0. Footnote: a fifth one-dimensional form, a self-dual form of lines in space called the regulus, will be defined in Chapter 11. This definition of the first four one-dimensional forms of the second degree is due to Jacob Steiner, 1796 to 1863. Attention will be called to other methods of definition in the sequel. Theorem 1. The section of a cone of lines by a plane not on the vertex of the cone is a point conic. The section of a cone of planes by a plane not on the vertex is a line conic. Now let A1 and B1 be the centers of two flat pencils defining a point conic. They are themselves, evidently, points of the conic, for the line A1-B1, regarded as a line of the pencil on A1, corresponds to some other line through B1. Since the pencils are, by hypothesis, projective but not perspective, and the intersection of these homologous lines is B1. The conic is clearly determined by any other three of its points, say A2, B2, C2, because the projectivity of the pencils is then determined by A1, A2, B2, C2, projective with B1, A2, B2, C2. By Theorem 17 of Chapter 4. Let us now see how to determine a sixth point of the conic on a line through one of the given points, say on a line L through B2. If the line L is met by the lines A1, A2, A1, C2, B1, A2, B1, C2 in the points S, T, U, A, respectively, figure 51, we have, by hypothesis, SB2T projective with UB2A. The other double point of this projectivity, which we will call C1, is given by the quadrangular set Q of B2ST, C1AU. Theorem 23 of Chapter 4. The quadrangle which determines it may be obtained as follows. Let the lines A2B1 and A1B2 meet in a point C, and the lines AC and A1C2 in a point B. Then the required quadrangle is A1A2CB, and C1 is determined as the intersection of A2B with L. C1 will coincide with B2 if and only if B is on A2B2. Figure 52. This means that AC, A1C2, and A2B2 are concurrent in B. In other words, A must be the point of intersection of B1C2 with the line joining C equal to A2B1, A1B2, and B equal to A1C2, A2B2, and L must be the line joining B2 and A. This gives, then, a construction for a line which meets a given conic in only one point. The results of the preceding discussion may be summarized as follows. The 4 points A2, B2, C2, C1 are points of a point conic determined by two projective pencils on A1 and B1, if and only if the 3 points C equal to A1B2 A2B1, B equal to A1C2 A2C1, A equal to B1C2 B2C1 are collinear. The 3 points in question are clearly the intersection of pairs of opposite sides of the simple hexagon A1 B2 C1 A2 B1 C2. Since A1 B1 C1 may be interchanged with A2 B2 C2 respectively in the above statement, it follows that A1 B1 C1 C2 are points of a conic determined by projective pencils on A2 and B2. Thus, if C1 is any point of the first conic, it is also a point of the second conic, and vice versa. Hence, we have established the following theorem. Theorem 2, Steiner's theorem. If A and B are any two given points of a conic, and P is a variable point of this conic, we have A pencil P projective with B pencil P. In view of this theorem, the 6 points in the discussion may be regarded as any 6 points of a conic, and hence we have Theorem 3, Pascal's theorem. The necessary and sufficient condition that 6 points, no 3 of which are collinear, be points of the same conic, is that the 3 pairs of opposite sides of a simple hexagon, of which they are vertices, shall meet in collinear points. The plain dual of this theorem is Theorem 3', Brianchon's theorem. The necessary and sufficient condition that 6 lines, no 3 of which are concurrent, be lines of a line conic, is that the lines joining the 3 pairs of opposite vertices of any simple hexagon, of which the given lines are sides, shall be concurrent. As corollaries of these theorems, we have Corollary 1. A line in the plane of a point conic cannot have more than 2 points in common with the conic. Footnote. Theorem 3 was proved by B. Pascal in 1640 when only 16 years of age. He proved it first for the circle and then obtained it for any conic by projection and section. This is one of the earliest applications of this method. Theorem 3' was first given by C. J. Brianchon in 1806. Journal de l'École Polytechnique, Volume 6, page 301. Footnote. The line thus determined by the intersections of pairs of opposite sides of any simple hexagon whose vertices are points of a point conic is called the Pascal line of the hexagon. The dual construction gives rise to Brianchon's point of a hexagon whose sides belong to a line conic. Corollary 1'. A point in the plane of a line conic cannot be on more than 2 lines of the conic. Also, as immediate corollaries of these theorems, we have Theorem 4. There is one and only one point conic containing 5 given points of a plane, no 3 of which are collinear. Theorem 4'. There is one and only one line conic containing 5 given lines of a plane, no 3 of which are concurrent. Exercises. 1. What are the space duals of the above theorems? 2. Prove Brianchon's theorem without making use of the principle of duality. 3. A necessary and sufficient condition that 6 points, no 3 of which are collinear, be points of a point conic, is that they be the points of intersection AB', BC', CA', BA', CB', AC' of the sides ABC and A'B', C' of 2 perspective triangles in which A and A', B and B', C and C' are homologous.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt 2019. Thank you for listening.